Hi guys, welcome to the Power DSP lessons. Today we start our lesson with the continuation of the previous episode. DFT works with an example in which we have seen how the DFT has worked on the time domain signal to bring the frequency information out. We have also come across the terms negative frequencies, magnified amplitude values at the output, and the phase angle. In today's lesson, we are going to see little bit more details on this. Let's get started. This is the spectrum for the example that we have seen in the last episode. We have fed 8 samples to the DFT and got 8 samples at the output. That is from sample index 0 to 7. In general, DFT gets n input samples and outputs n samples. The sample index is running from 0 to n minus 1 at both the input and output. We can see 1 kHz and 3 kHz components in the spectrum. The useful information is present between 0 to Fs by 2. The sampling frequency Fs here is 8 kHz. So the useful information is present from 0 to 4 kHz. That is from 0 to n by 2 samples. The samples from n by 2 plus 1 to n minus 1 are called negative frequency components. In this example, samples 5 to 7 are negative frequency components. As we know, the frequency spectrum of a discrete signal is periodic. That makes the negative frequencies between n by 2 and n minus 1 same as between minus n by 2 and 0. The negative frequencies are redundant information, and the information that is present between 0 to n by 2 is a useful one. Now we are going to see why the magnitude values are amplified at the output. The frequency domain is defined as spectral density. Spectral density is nothing but amount of amplitude present per unit bandwidth. To convert the amplitude into spectral density, we need to divide each amplitude by its bandwidth. If the signal is real, the useful information is present from 0 to n by 2 samples. So the total bandwidth is n by 2 and the bandwidth of each sample is 2 by n. Spectral density magnitude is equal to amplitude divided by its bandwidth of 2 by n. So the output of the DFT is amplified by n by 2 if the signal is real. If the input is complex sinusoid, the output of the DFT is amplified by n times. Our example uses a real sinusoid, so the amplitudes are amplified by n by 2 times. N is 8, so the amplified by 4 times. Next, we have to understand what the phase angle indicates at the DFT output. In this example, 1 kHz sine component gives the phase angle of minus 90 degree. What does that mean? Actually, it indicates the phase difference with respect to 1 kHz cosine wave. This is the 1 kHz cosine wave and it is 1 kHz sine wave. Of course, we are taking only one cycle here and we can see the phase difference as 90 degree lagging, that is minus 90 degree. Similarly, the 3 kHz component, which is already phase shifted by 45 degree, is now offsetted in phase by 45 degree with respect to the 3 kHz cosine wave. The 3 kHz sine component is lagging, so it is minus 45 degree. If the component is leading with respect to cosine, then the phase angle would be in positive. So in general, the phase angle gives an idea how the particular frequency component is shifted in phase with respect to cosine wave with the same frequency. Okay guys, that's all for today's lesson. Meet you in the next lesson. Until then, bye bye.